More than 80% of this engine, by weight, was never machined or welded. It was grown layer by layer from metal powder and laser light until something that used to take years came together in a fraction of the time. Picture a rocket engine built like a single-poured block of steel, not a machine bolted from 1,000 smaller ones. That engine is the TH-11, and it just carried a private Chinese rocket into orbit on its first attempt. This is not a prototype behind glass. It is a certified flight, confirmed on the Tianlong 2's 2023 debut. You know the feeling of waiting months for a part that should have taken days. Let me tell you what that means in plain English, and that is just the beginning. Printing the parts was the easy problem. Hit subscribe. By the end, you will understand exactly why NASA has not managed this yet. Space Pioneer's TH-11 didn't get its printed parts in its compressed development cycle by accident. Someone had to bet a company on the idea that the entire discipline of rocket engine manufacturing was solving the wrong problem. That someone was Kang Yonglai. Here is what the industry believed for decades. A flight-qualified liquid rocket engine is not one part. It is hundreds of them. Combustion chambers, injector plates, turbo pumps, valve housings, each machined separately, each welded or bolted to the next, and each one a fresh opportunity for something to go wrong. Traditional development cycles for a new engine commonly ran 3 years or more, largely because every joint, every seam, every fastener had to be individually manufactured, inspected, and requalified before the whole assembly could even be tested together. NASA and Aerojet Rocketdyne once needed close to a year to fabricate a single rocket injector using conventional machining. One component, not a whole engine, sitting on a bench for the better part of a year before it was even ready to be bolted to anything else. That is the scale of the ceiling everyone accepted as physics rather than habit. Picture building a watch from 1,000 tiny parts, where a single loose screw anywhere in the mechanism can stop the whole thing cold. Now imagine that watch has to survive temperatures hot enough to melt the workbench it was built on. That was rocket engine manufacturing for half a century. Slow by design, because slow was assumed to be the price of reliability, and nobody with a functioning rocket program had seriously questioned the assumption. Kang Yonglai had already lived inside that system. Before founding Space Pioneer in 2019, he was the Chief Technology Officer at Landspace, one of China's first-generation commercial rocket companies, where he watched the traditional machining and assembly model up close, year after year, engine after engine. Most people who write about this industry never get to the part where the frustration actually started. And for Kang, it started with watching promising engine designs get bottlenecked, not by physics, but by manufacturing logistics. Backlogged machine shops, inspection queues, and welding schedules that had nothing to do with whether the underlying engineering was sound. His stated goal in leaving to start his own company was blunt: build engines fast enough and cheap enough for commercial launch cadence. Not government timelines stretched across years of machining backlogs. He was not trying to make an incrementally better engine. He was trying to remove the thing that made engines slow in the first place: the sheer number of separately manufactured parts and every hour of labor and inspection those parts demanded. That bet would eventually put Space Pioneer's engine at the center of a story far bigger than one company. But first, other people in China had already tried something like it and gotten laughed at for the attempt. China's early commercial rocket industry had already flirted with 3D printing years before Space Pioneer's engine ever hot-fired. Small companies had begun trying to print individual components, brackets, valve housings, the occasional combustion chamber, as a cost-saving experiment, and the stated goal was modest: shrink lead times on the easy parts while leaving the dangerous parts to conventional machining, the same way an automaker might print a plastic dashboard clip before ever trusting a printed engine block. The skepticism came fast. Printed metal was viewed as fine for structural brackets and fine for small thrust engines with forgiving tolerances. It was not viewed as viable for anything that had to survive sustained combustion pressure at scale, where a microscopic flaw in a printed layer could propagate into a crack under repeated thermal cycling. Rocket Lab had already proven printed components could fly, with its Rutherford engine reaching orbit repeatedly, but Rutherford sat in a modest thrust class, and industry voices were quick to draw a line there. Printed parts for a small pump? Fine. Printed parts for a full high-thrust engine core? Not yet. They said the same thing about jet engine turbine blades a decade earlier. Aviation manufacturers dismissed additive manufacturing as a novelty for prototypes, not flight-critical hardware, right up until printed turbine components became standard across the industry within years, quietly showing up in engines millions of passengers now fly on without a second thought. We all know how that ended. What Space Pioneer attempted went further than anything on the table at the time, not just printed brackets or a printed pump housing bolted to a conventionally built chamber. A fully closed-cycle engine, the kind that recycles its own exhaust back through the combustion process under extreme heat and pressure, built with printed components making up the overwhelming majority of its mass. Here's where the story really begins, because closed-cycle combustion is widely considered one of the hardest problems in liquid rocket propulsion, and nobody had tried building one primarily through 3D printing before. The engineering community's skepticism was not unreasonable. A closed-cycle engine already runs hotter, under more pressure, with tighter margins than almost anything else in propulsion, which is exactly why so few engine makers worldwide have ever attempted one at all, printed or otherwise. Layering an unproven manufacturing method on top of that was, to most observers, exactly backwards. Solve the printing problem first, on something simpler, before attempting the hardest combustion architecture in the field. Space Pioneer did not do it in that order. And that decision is where the actual mechanism of this story begins. Not with a spreadsheet full of cost savings, but with a question about how you print something that has to survive its own fire, finding its way back into the chamber that made it. Here's the problem with building a rocket engine, the traditional way. Every internal passage, every cooling channel, every injector port, every fuel line snaking through the chamber wall has to be machined separately, then welded or bolted to the next piece, and every one of those joints is a place where a seal can fail under pressure. Picture pouring a single block of wet concrete instead of stacking 1,000 individual bricks and mortaring each seam by hand. One version has failure points everywhere, hidden inside walls where nobody can inspect them once the engine is sealed shut. The other has almost none. That is the plain English version of metal 3D printing. A laser melts fine metal powder layer by layer, fusing each thin slice to the one beneath it, building a solid part from the inside out rather than assembling it from separately made pieces. There is no seam to inspect later because there was never a seam to begin with. Complex internal geometries, the exact kind of twisting cooling channels a closed-cycle engine needs, can be printed as one continuous piece instead of welded together from smaller sections, geometries that would have been nearly impossible to machine conventionally in the first place. This was the exact problem Kang Yonglai had been circling since his days at Landspace, watching machining backlogs slow down otherwise promising engine designs. Reducing part count was not a nice-to-have efficiency gain in his plan. It was the entire premise Space Pioneer was founded on, the single idea the rest of the company's engineering roadmap was built around. The consequence showed up in the numbers. More than 80% of the TH-11 engine's parts, by mass, ended up 3D printed rather than machined and assembled. Entire categories of weld seams and fasteners removed from the design before the engine ever reached a test stand. The development cycle that traditionally stretched past 3 years, compressed by roughly 3/4, according to figures the company has published, turning a multi-year manufacturing campaign into something closer to a single development season. Fewer parts, fewer joints, fewer chances to fail. That single sentence is the whole mechanism, and it explains why printing solved the cost and time problem that had bottlenecked engine development for decades. But cutting part count only addresses how fast and how cheap an engine can be built. It says nothing about whether a printed structure can survive the single hardest job inside a rocket engine, routing its own white-hot exhaust back through itself without cracking apart. That problem was still sitting there, unsolved, and solving the easy half first did not make the hard half go away. Here is the brutal catch that part count reduction alone could never solve. Most rocket engines are open cycle, meaning they bleed off a portion of unused fuel and oxidizer to spin the turbo pumps, then dump that leftover exhaust overboard, wasted. It is simpler and it is forgiving, which is exactly why most commercial engines are built this way. A closed-cycle engine does something else entirely. It routes all of that leftover propellant back through the combustion chamber, burning it a second time to maximize efficiency, which means every printed channel inside the engine now has to survive exhaust gas at extreme temperature and pressure, flowing back through structure that has never been welded shut. Printed metal, already viewed with suspicion for structural reliability, was now being asked to survive the single most punishing thermal environment in the entire engine, repeatedly, without the reassurance of a weld seam anyone could point to as proof of strength. What if you solve both problems at once instead of one at a time? That is the paradigm break Kang Yonglai's team made. Rather than proving printed parts could handle simple structural loads first, then separately proving a closed-cycle architecture could work with conventional manufacturing. Space Pioneer built an oxidizer-rich staged combustion engine, the TH-11, with its most critical internal channels printed from the start, betting both unproven ideas on a single design. His own engineers reportedly told him this was the wrong order to attempt it. Solve printing on something simple first. Solve closed-cycle combustion on something conventionally built first. Kang bet the company's entire first-flight vehicle on doing both simultaneously, betting that separating the two problems would only slow Space Pioneer down without reducing the actual risk, that the risk was already there whether the engine was built in stages or all at once. It sounds like it should not work. That is exactly why it does. Full system hot fire testing confirmed the printed closed-cycle architecture, performed to specification well before the engine ever left the ground, reaching a thrust-to-weight ratio of 130, a figure that puts it among the more efficient engines in its class, regardless of how it was manufactured. Printed, closed cycle, both at once. Nobody had put those three words together and expected a working engine. Mechanism surviving a bench test is one kind of proof. What came next was an entirely different kind of pressure, putting that same engine inside a real rocket on a real launch pad for a flight where there would be no second attempt if any of it failed. For most of the industry's history, a new rocket engine spent years being qualified in complete isolation, hot-fired on a stand, torn down, inspected, rebuilt, and fired again dozens of times, long before it ever touched a full vehicle stack. That old approach treated engine qualification and vehicle integration as two entirely separate multi-year problems, stacked one after the other, each with its own testing campaign and its own approval process. Here's what most people get wrong about what Space Pioneer actually did differently. It was not just printing an engine, it was compressing the gap between engine validation and full vehicle flight into a single, tightly coordinated development timeline, rather than treating them as sequential, multi-year phases that had to be finished one before the other could begin. Think of it the way modern navigation software reroutes a driver in real time using live data instead of a fixed route planned months in advance. Traditional engine qualification was the fixed route. Years of predetermined testing before anything moved forward, regardless of what the early results actually showed. Space Pioneer's compressed approach fed hot-fire data directly into flight readiness decisions on a dramatically shorter timeline, adjusting as results came in rather than waiting out a rigid, multi-year sequence built for a different era of manufacturing. The scale of what this enabled was real. Tianlong 2 became the first rocket from a private Chinese company to fly using liquid propellants rather than solid ones. A meaningful architectural shift, since liquid engines are what make reusability realistically achievable down the line, unlike solid fuel motors that burn once and cannot be reused. A single TH-11 engine powered the vehicle's second stage, carrying a small satellite toward a sun-synchronous orbit, a precise target that leaves little room for error in either the engine or the timeline that produced it. Engineers who worked on programs like this will tell you the coordination problem is usually harder than any single component. A perfectly printed engine means nothing if it cannot be integrated, tested, and cleared for flight on a timeline that makes the whole company viable. An engine that works on a test stand but arrives too late to matter is still a failure, just a quieter one. The printed engine and the compressed development timeline work together, not separately. That is the actual system Space Pioneer built, and neither half of it would have mattered without the other. The combined result of a majority-printed closed-cycle engine and a radically compressed integration timeline was a number precise enough that it needed independent verification before anyone outside the company would believe it. A successful orbital insertion on the very first attempt of a fully liquid-fueled Chinese commercial rocket. Here is the honest picture. A single successful flight does not prove a printed, closed-cycle engine is ready for mass production, and Space Pioneer has been candid that reusability, the ultimate goal behind choosing liquid propellants in the first place, is still a target, not yet a demonstrated capability. Printed engines still require rigorous inspection protocols before wider adoption, and qualifying that inspection process at scale across hundreds of engines rather than one remains unfinished work that no single flight can settle on its own. With that trade-off acknowledged, here's what actually happened. On April 2nd, 2023, Tianlong 2 lifted off and placed its payload into its targeted sun-synchronous orbit on the very first attempt, making Space Pioneer the first Chinese private company to successfully fly a liquid propellant rocket. The satellite aboard, developed to test remote sensing capabilities, reached orbit exactly where it was supposed to, with no second attempt required and no margin left over to explain away. That is not a qualification milestone. That is a company betting its first orbital flight on an engine architecture nobody had built quite this way before and winning outright on the only attempt that actually counted. Most first flights in this industry are not expected to succeed cleanly. Plenty of established rocket programs have needed a second or third attempt just to reach orbit at all, let alone the exact target orbit specified beforehand. For Kang Yonglai, this was not an abstract engineering achievement. This was the direct answer to the decision he made walking away from land space in 2019. The bet that part count reduction and closed cycle combustion, solved together rather than in sequence, could get a private company to orbit faster than anyone thought possible. The engine did not just work. It answered the exact question he had built a company to ask on the exact timeline he had bet the company could achieve. 80% printed. Closed cycle. Orbit on the first try. That is the sentence the entire program was built to earn. If a closed-cycle engine surviving its own recycled exhaust on the first orbital attempt surprised you, the next part of this story is going to be even harder to believe. Hit subscribe so you are there when we cover it. What Space Pioneer proved was not a curiosity confined to one company's launch pad. It raised a question every rocket engine manufacturer on the planet now has to answer for itself, whether they were ready for that question or not. Because the excuse that printed closed-cycle engines were too risky to fly no longer holds up against a flight record that says otherwise. The real bottleneck in global launch access has never really been rocket science in the purest sense. It has been manufacturing throughput. Every commercial launch provider on the planet is chasing the same problem. How many engines can you build, qualify, and fly in a year at a cost small satellite operators can actually afford, without stacking up a backlog of half-finished hardware waiting on machine shops? A method that cuts development cycles by 3/4 and removes entire categories of weld failure points changes that math for anyone willing to adopt it. Small satellite operators, launch providers, and propulsion manufacturers across the industry are now re-evaluating their own manufacturing pipelines in light of what a printed closed-cycle engine has demonstrated is achievable. Rocket Lab and Relativity Space had already pushed printed components into flight hardware. Space Pioneer's result pushes the ceiling further toward full closed-cycle architectures rather than simpler engine types that ask far less of the printed metal involved. Here's what adoption actually requires, and why it is harder than copying a design. Printing capacity at the necessary scale, certified aerospace-grade metal powders, and inspection protocols capable of catching internal defects in a part that was never welded together in the first place. All of that has to exist before any other company can simply replicate this result. That is a manufacturing and materials science barrier, not a patent anyone could license their way around. And it is precisely the kind of barrier that takes years of quiet infrastructure work rather than a single clever design choice. A competitor cannot shortcut it by hiring away one engineer or reading one technical paper. The printers, the certified powders, and the inspection equipment all have to exist in the same facility at the same time before any of it produces a flight-ready part. The aviation industry lived through an almost identical underestimation. Turbine blade manufacturers dismissed additive manufacturing as unsuitable for flight-critical components for years, only to see printed turbine parts become standard equipment across commercial jet engines within roughly a decade of that dismissal, powering aircraft that now carry passengers every day without anyone on board giving it a thought. The limitation in both cases was never political and never about which country or company got there first. It was a materials and manufacturing ceiling, and ceilings like that get broken by whoever solves the engineering problem, not by whoever makes the loudest claim about it. And if replacing how a rocket engine gets built sounds significant, wait until you see what happens when the exact same engineering mentality gets pointed at an engine you might actually be driving. Before we get to the zoom out on this one, if a manufacturing breakthrough inside a rocket engine caught your attention, the same relentless engineering logic just showed up somewhere far more familiar. I already covered China's genius 48.41% engine breakthrough shakes, the entire car industry, where a completely different kind of engine broke a thermal efficiency ceiling that had capped internal combustion for over a century. That one is worth your time. Here is the actual zoom out. What Space Pioneer proved is not just that printing can build a rocket engine faster, it proved that two of the hardest problems in propulsion, reducing part count and surviving closed-cycle combustion, can be solved together in the same design on a company's very first flight, rather than solved one at a time across years of separate programs. That changes the calculus for every launch provider deciding whether printed engines are a novelty or the new baseline for how engines get built going forward. If you made it this far, you now understand more about how modern rocket engines get built than most people who write about spaceflight for a living. Not just that printing is faster, but why solving two hard problems at once turned out to be safer than solving them one at a time. Here is what was actually proven. A closed-cycle liquid rocket engine, built from components that were never machined or welded in the traditional sense, survived its own recycled exhaust and carried a Chinese commercial rocket into its exact targeted orbit on the first attempt, with no second chance built into the plan. Kang Yonglai left a first-generation rocket company to bet that manufacturing, not physics, was the real ceiling holding the industry back. He built a company around that bet, printed an engine nobody else had attempted to print quite this way, and watched it fly to orbit on the first try. That is what the bet cost him to prove, and that is what it earned him. A working answer to the exact question he left Landspace to ask. If this changed how you think about what 3D printing can actually survive, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should aerospace regulators fast-track certification for printed engine architectures like this one, or is a slower, more cautious qualification process still the right call given what's actually at stake if one fails? I read every single one. See you in the next one.